Any complex linear operator can be systematically dismantled into simpler, independent pieces. To do that, we look directly at its polynomial structure. Look at this factorization of the minimal polynomial. We break it down into a product of distinct prime factors, where p of x equals p1 of x to the r1 times p2 of x to the r2, all the way up to pk of x to the rk. The core mathematical requirement here is that these polynomial chunks are relatively prime. They share no common roots, meaning each block operates entirely independently of the others. If we swap the algebraic variable x for our geometric operator t, we can define a set of primary components. We call these components wi. Each wi is simply the null space created when we apply a specific polynomial chunk, pi of t to the ri, to our vector space. That means each wi acts as a geometric bucket. It holds all the vectors that get completely destroyed by that specific polynomial block. Because the mathematical blocks are independent, the resulting geometric buckets are independent too. Now we can translate that algebraic factorization into a physical splitting of the vector space. This diagram shows the entire vector space V perfectly split by those polynomial roots. It is defined as the direct sum of W1, W2, and so on, joined by the direct sum symbol. This symbol tells us we are looking at an invariant direct sum. When the operator t is applied to any vector inside W1, the resulting vector never escapes W1. T never mixes vectors between these independent buckets. By ensuring the vectors stay trapped in their respective spaces, we can ignore the massive, entangled matrix. We can now study it as a series of small, completely isolated blocks. Let's look at the special scenario where the minimal polynomial factors entirely into simple linear pieces, like x minus c. This equation brings us to theorem 13. When all the factors are linear, our operator t splits perfectly into two distinct operators. T equals d plus n. D represents the diagonalizable part. It acts like a clean scalar. N represents the nilpotent part. A nilpotent operator is one that eventually multiplies to 0, where n to the power of k equals 0. For this decomposition to work, there is a crucial mathematical requirement. These two operators must commute. D times n must equal n times d. Think about what happens on a subspace with only one eigenvalue, c. The operator d behaves purely as a flat scalar, c times the identity matrix. That clean behavior systematically isolates all the messy shifting transformations entirely into the nilpotent operator n. We can step out of abstract geometry and apply this exact same theorem to continuous functions and differential equations. Look at this split screen. If we assign our operator t to be the derivative operator d, our target problem becomes finding the null space for the differential equation where d minus c times the identity, all to the power of r, applied to a function f equals 0. In the base case, where r equals 1, we are looking for the functions destroyed by d minus c times the identity. Solving the derivative of f equals c times f perfectly yields the exponential function, e to the power of ct. When we expand the solution to the full power r, the null space is spanned by an expanded list of basis functions, e to the ct, t times e to the ct, all the way up to t to the r minus 1 times e to the ct. We have exactly r independent basis functions. The algebra of the polynomial has directly dictated a geometric dimension of exactly r, proving that this solution space is a perfectly invariant geometric structure under differentiation. Let's bring these core concepts together to review the mechanics of the primary decomposition theorem. This cheat sheet outlines the rules. First, operators decompose based on relatively prime polynomial factors. Second, each primary component acts as an isolated, invariant geometric bucket. Finally, if factors are linear, the operator splits perfectly into a diagonalizable and nilpotent part. To master the step-by-step proofs behind these concepts, reference the foundational text, Linear Algebra by Hoffman and Kunze. Like and subscribe for more deep dives into higher mathematics.